Hey guys, so we'll continue our reinforced concrete lectures. Today I'm gonna touch base, just brief introduction about what's the development link, what's the definition. I'll show you one formula for how the ACI code calculates how much the required development link for straight bars in tension. So it depends on the bar shape and whether it's tension or compression. So you can tell. So straight bars in tension, hook bars in tension, or bars in compression. So there's different formula for each of them. Each require more development in order for us to provide enough development link. And what's the development link? I'm going to explain it to you in a minute. That's going to take about 20 minutes from this lecture. Then I'm going to give you a full example on how to calculate or check the deflection, with some review to what we had with the flexural design. I just also taped yesterday, is it online or not, a lecture, one example 50 minutes on how we check the deflection for rectangular beam. So today's example will be how we check the deflection for TV, for a TV. Also in that example, it's a complete design too. Okay, I designed the flexure first, then I showed how to calculate I effective and the deflection, and how you check the associated ACI limit on the deflection, the live load deflection.
You said that's
it will be soon. Hopefully you will have this last lecture and today's lecture before this Friday, if possible. Thank you so much, Gerard. You know, he's doing this voluntarily and he already took this class, but he's here to help us. So development. Length. Sometimes it's called embedment length. Embedment length, which is in the book we are using, is chapter 6. It's chapter 6 in the book we are using. And what's development length? What's the development length? Or it's the anchorage length, or embedment length. Think about it. It's how much you need to plant the steel bar in the concrete so that you have enough length in there to develop the full capacity you want from the bar. Okay. Now look, when we design this tension steel, in our design to calculate, they are for flexural design, right? So they are supposed to give us Vmn. And when we calculated Vmn, it was V As Fy D minus A over 2. So how much they are supposed to be stressed to? As Fy, how much the stress? Fy. So they're supposed to develop their full capacity. They're supposed to yield, right? So now look, if these bars will be pulled out from the concrete, the bond is lost with the concrete before they give you Fy, that means your flexural design is wrong. Because in your flexural calculation, you calculated the strength, the flexural strength, based on these tension bars, will give you Fy. Also the compression bar, if we have doubly reinforced section, almost it's Fy. It's something very close, Fs dash, very close to Fy. Okay? So these bars should be able to develop the full capacity, which is Fy. Where at the section that you wanted to calculate Fy, let's say at the maximum moment region. That's how we design, with the maximum moment region. These sections must give you Fy, and somewhere else. Good? So now look at this. If you have a beam like that, this will make it clear. If you have a beam like that, it's a semi supported beam. So we expect that the reinforcement to be where? At the bottom, right? This is the steel. At the bottom. You have 1 bar, 2 bars, 3 bars, 4 bars. But this is the level of the steel. This is the level of the steel. Okay? See this bar here? These bars? How much the stress in these bars here? You know what I'm drawing now here? This is the bar. This is the stress in the bar. how much the stress in the bar as we go within the length of the beam. At the end of the bar here, is there any stress? Zero stress. There is no bending here. Anyway, there is no bending here. There is no moment. There is no moment. That means there is no Fy. So it's traction free. Zero stress at the end of the bar. So the bar here has zero stress. Right? The bar is planted in the concrete. They are composite material. Through the deformation, we have the assumption of full bond between the concrete and the steel. So the bar now starts developing tension. Tension stress. Tensile stress through the bond with the concrete. Right? So the stress, I'm saying, the stress will keep increasing, right? As we go. Once you hit Fy, can the bar develop more stress or a stress larger than Fy? No, that's the yield. So the stress will be constant. Now, any idea? What should I say? So how much it took? What's the length that it took for the bar to develop Fy? That's the development length. That's the required development length for the bar to develop its capacity. That's how much the bar must be inserted or planted within the concrete to give you Fy. Now, this is how they do the test, guys. It's not something. It's not a magic. They cast a big block of concrete. They pour a big block of concrete or a wall. They bring different diameters of bars. Okay? Let's say that now today they want to study number 6. And this number 6 they're going to study with paint or epoxy coated or not epoxy coated. Okay? So they bring like epoxy coated bars, not epoxy coated bars of number 6. They bring the first one, they plant it in the concrete 10 inch. They cast the concrete develops strength. Now it's planted in the concrete hardened. The second one they put 20 inch. The third one they put 30 inch, 40 inch, 50 inch, from the same series. Then they go to the one with the epoxy. Same. Then they bring a machine, pull-out machine, direct tension machine. Okay? And they have a strain gauge on the bar inside to measure how much the strain in the bar. And they pull each one of them. The length at which the strain in the steel read epsilon y, that's the development length for each series. They repeat the situation for the other bar diameters, for other epoxy coated, for lightweight concrete, for larger strength concrete. Someone did this already in the research, and that's what you have in the ACI code. Okay? Now, to calculate the development length is something easy. It's just one equation. Will give you the development length based on the size, based on the conditions you have, all of this thing. So you will be able to calculate something called development length for inch. The issue is how you apply it to the real beam, how you implement that in the real beam. Okay? So I'm going to show you now what's the formula, what's the ACI equation for the development length. Then I'm going to explain this to you through the example that we're going to start about the deflection, then we move to this thing here. This is the ACI formula. LD equal 3/40 Fy over lambda square root of prime C psi T psi E psi S over CB plus KTR over dB. See all of this here is a factor multiplied by the diameter of the bar. Everything in here is multiplied by dB. What's this required development length? That's the ACI requirement for development length for bars. Here, straight bars bars in tension. Straight bars in tension. That's the maximum development length you may calculate when the bars are straight and in tension. If the bars are straight but in compression, the development length will be smaller. The required development length is smaller. Why? Because in tension there will be cracking. So you will require higher length, higher embedment length to develop a foil. Now, what if we can't accommodate this requirement? You need 50 inch and we don't have this space. You say, okay, I'm going to terminate my bars into a standard hook. There are standard hooks, 90-degree hook, 180-degree hook. If you do that, the development length becomes much more smaller than the required development length for the bars in tension. Not only that, you can say, you know what? Oh, I can tell. I can increase the concrete strength. If I increase the concrete strength, this will be lower. Right? Because it's at the bottom, it's at the denominator. Okay? That's one thing. Now, these are easy things, guys. They are so easy. In the book, I think it's in it's available and there's a full explanation to each of them. But they are easy. Is there any problem with Fy? Anytime you see lambda in the ACI code, it's the lightweight factor. If you are talking about normal weight concrete, lambda is 1. But they put in the equation because to have one generic equation for lightweight or normal weight concrete. So if it's normal weight concrete, lambda equal 1. If it's a lightweight concrete, 0.75 for lightweight concrete. Lightweight concrete. And sometimes if the splitting tensile strength of lightweight concrete is specified, there is a way to do it, but you don't have to follow that procedure. The lambda will be lambda equal FCT divided by 6.7 square root FCM, less or equal 1, of course. This is the splitting tensile strength of the lightweight concrete, and this is the compressive strength of lightweight concrete. If the compressive strength is given and the splitting tensile strength is given, you can calculate lambda from, it's allowed. Or you just take it 0.75 and you are done. Good? So normal weight concrete, lambda equal 1 for normal weight concrete. So that's lambda. I'm going to come. Is there any problem with the diameter of the bar? That's the diameter of the bar you are calculating how much this bar needs to be to have a development length. So this is given to you. Psi T. It's a factor. It's a factor. These all of them are factors. T is top or bottom. It's a location factor. Location factor. It says it's casting position factor. Where is the location of the steel? Is it at the top or the bottom? They are saying more than 12 inch of fresh concrete is placed below reinforcement. Other situations. The first other situation is one. Look. Psi T. More than 12 inch of concrete below the bars. Psi T equal 1.3. This is not the case. Psi T equal 1. So for a bar to have 1.3, first of all, it has to be top bar. It has to be top bar. It means negative moment location. We're talking about bars in tension. Top. If the depth below that bar is 12 inch or more, psi T is 1.3. For bottom bars, regular bars, at the bottom, you won't have more than 2 inch, the cover, 2.5 inch. So it will be 1. Good? So that's psi T, the T is for top, bottom. If you want to memorize it. What does it mean, so if you forget it? E, epoxy or not epoxy? E, epoxy or not epoxy? Says epoxy coated or zinc and epoxy dowel coated bars or wires with cover less than 3 dB or clear spacing less than 6 dB, 1.5. Other epoxy coated conditions, 1.3. Non-epoxy coated, 1. Okay, it's all written in the book, very clear, and you will have it open sheet or open book for the exam, or anytime this will be available for you. Again, if it's no non-epoxy coated bar, what's psi E? 1. Non-epoxy coated psi E is 1. Most of other epoxy coated conditions, 1.3. For some situations, some epoxy, once there is some requirement in terms of the cover is less than 3 dB or the clear spacing less than 6 dB, this can go up to 1.5. This can go up to 1.5, rare situations. Okay? So this number, psi E, is either 1.5, rare, 1.3 if it's epoxy, or 1 if it's non-epoxy. If I tell you non-epoxy, it's 1. Now look, the code says there is a limitation also on those two together. On those two together, psi T times psi E must be less or equal 1.7. You know now, look at this. So psi T is how much the maximum value it can get? 1.5. Psi T, I say 1.3. This guy here can have 1.5 or 1.3 or 1, right? Other than 1.5, this is done. Other than 1.5, this is it. If you have 1.5 for psi E and 1.3 for psi T, the multiplication is more than 1.7, right? So you take 1.7 for both of them. They're saying this is too much exaggeration. Understood? So psi T location, top or bottom, psi E, epoxy or non-epoxy, psi S, size factor. So easy, look at this. Number 6 and below, 0.8. Number 7 and up size bars, 1. Number 6 and below, this is 0.8. Take psi S equal 0.8. Number 7 and up, 1. But the codes after that, this is the code requirement. They say, the code people, they say, we encourage you to take it 1 all the time. For all bar diameter. They say, it's recommended to take it 1. Okay? But look, if you take it 0.8 for bar size number 7, and you have a problem, then you are liable. As long as you are above the minimum code requirement, you are fine. You just conserve it. Again, psi S is a size factor. 0.8 for number 6 and below, 1 for number 7 and up, but the code encouraging using 1 for all bar sizes. Done? Now look at this here. Any problem with dB? This we take it as together. It's one factor. Together. Is there any problem with dB? That's dB. KTR. Okay, I'm going to read for you. Transverse reinforcement index. It's an index depend whether you have a transverse reinforcement within the development link or not. Usually you don't have this information. Usually you don't have this information. And it has annoying formula, but there is a formula you can calculate that one. And the chance to make a mistake in that formula is a lot. However, the code tells you, and then you are allowed to take KTR to be 0. The code tells you, you are allowed to take KTR equals 0. Take it equal 0, I'm telling you from now. Take KTR equals 0. I'm going to tell you also why in a minute. Now, CB. CB is the lesser of the two. The cover, either side or bottom cover to the center of the bar, or half the distance between the bars, center to center. CB is either this, the smaller or the lesser of the two, either this or half of this, the lesser of the two. That's CB. Good? Now, in no case, this magnitude here should be greater than 2.5. CB plus KTR over DB less or equal to 2.5. That's why sometimes you spend a lot of time and effort calculating KTR and making a lot of assumptions. And at the end, this by itself, you're going to end up exceeding this limit. So you go back to this limit. So if you have a cover of 2 inch, right? That's a typical cover, 2 inch. Okay? For number 7 bars. For number 7 bars, 2 divided by 7/8. So you are almost there. For number 8 bar, you have 2, which is fine. Okay? So you have everything now. Now you can calculate something called how much the required development length. So calculating the development length, guys, is a step. Straightforward, based on what's given for you. Straightforward, it's an equation, you just apply it. After you get all of these terms, things will be very specific for you. If nothing is obvious, like nothing about epoxy or not epoxy, you can assume. Or you say in your report, for if the bars to be epoxy, LD is that much. Non-epoxy, that much. Or my assumption were based on non-epoxy coated. If the bars will be epoxy coated, I need to review this one. The engineer need to review all the development length requirements. Okay? So, but usually the information, all the information are given to you. Okay, guys? So now you can calculate the development length. How to apply or to check if you remember here the reinforcement is good or not, you will see in the example. Okay, guys? So this is straight bars and tension. On Monday, I'm going to cover, or I may tell something before that, a video. Bars and tension, bars and compression, and hooked end bars. Hooked bars. Any question? I have like 20 seconds till I finish erasing this. Any question? So you understand what's the development thing, guys? See this simple fact here? Not many understand. A lot of guys, they don't know how to calculate, they have their Excel sheet, but they have no clue what does it mean. They have no clue what does it mean. Guys, look, if you take 1 bar from the concrete, this is what you see. This is your bar, right? This is your bar from the concrete. Does it have tension from here? Is it in tension? Yes. So this is what? T1. Is it the same tension here? It's not. Is the moment here equal the moment here? In any beam, is the moment to the left equal the moment to the right in any location? Of course not. The moment is changing. Unless you have a constant moment, let's say. So the moment here is different than the moment here. So this T2 usually is greater than T1. Usually we have here, if this is close to the support, this is 0. So for this balance, you need to have something coming from friction. Bond stresses, some kind of a shear. Over what? Over the width. Over the width. Over this area. That's the concept of development length. This must be enough length here so that the bar can develop its intended stress at this location or its full capacity. To give you another example. Then I move to that. Look, if you have a cantilever beam, that's a cantilever, right? For a cantilever, what's this support supposed to be? Fixed. For a cantilever, this is fixed, right? So the loading, the moment is negative. So the reinforcement is at the top. It's tension, right? Right? So that's your reinforcement. when you design this cantilever beam, you take your moment, for what moment you design? For the maximum moment. Right? Which is here, the cantilever. Right? So when you design these bars, the number of bars you need in here, that was based on maximum negative moment. So do you leave them like this? This bar, these bars, supposed to give you a Fy here. So you can say, oh, no, but they do that. Because if I go from this way, it's good. What if I go from this way? Where these bars are supposed to give me a Fy. Do we agree about this one here? They must develop a Fy here. To the right and to the left, they must have enough development length. So they must be embedded in here so that this length can give me a Fy in here, enough to develop a Fy in here. Now, sometimes the support is narrow or small. Will not give you enough length if you do the straight bars and tension. So you see the hook. This is a standard 90-degree hook. Could be 180. These are standard values. How much you go, how much the turn. These are standard values, will be fabricated for you. So now this length must be checked. This width of the support must be checked against something we calculate for LDH, development length for bars developed into a standard hook. Okay? Okay, guys? So you understand now? And from here to here, this distance from here to here must be greater than LD because they are straight bars. The hook is for this side. There's no hook here. Okay, yeah, look. If our design called for 4 bars, everybody, if we require 4 bars for this cantilever, okay, so the design, those bars are 4 bars, number 7, number 8, whatever, 4 bars. That's what the design called for. After we did finish flexural design, because when we check the development length, when do we check it? After everything, right? So you have 4 bars. Good? Now I tell me where is the location where I can stop the 2 middle ones. So in other words, I'm going to just show you for demonstration. Those are the 2 middle 2. They are the same level, but just I'm doing this to show you, right? You know, you understand this, right? Those are the same location, but just to show you. So those are 2 number 8, let's say. Here this is 4 number 8, for example. And those are the other 2 number 8. This brings a new concept to you called the cut-off points, where I can stop 2 of them. From the left is good. I checked it for everything. Now from the right here, if I want to stop them, this length here must be greater than LD. I can't just stop them a short distance here. The distance that I will stop them here must be greater than LD, which is a number we will calculate. I told you, LD, calculation of LD is a number, an equation, guys. How you verify it now with things here become complicated. Now this is it. This distance here, from here to here, greater or equal LD. What if, I'm going to show you how we determine this one. What if this one is greater than LD? Good. What if this one is less than LD? You use LD. You have to use LD. Now, how we determine the location where we can cut 2 bars? Theoretically. From where? From the moment diagram. Because look, why we use 4 bars? So that we have 3 mm here greater than ultimate here, right? Now, what do you do now? You calculate the strength of your section for 2 bars. You calculate the strength of your section for 2 bars. You can calculate 3 mm for 2 bars only. You go to your moment diagram. You find where is the location where now the moment becomes that thing. That's the theoretical cut-off point. At this point, no, you can terminate 2 bars. cut-off point, termination of bars. See, right? When 2 are enough, the answer is when 2 are enough. Why do you need more? The moment diagram, the moment is decreasing. Why would you need to continue the 4 all the way? Like, this is what you see, guys, realistic. If you have a beam with 16 bars, are you going to continue the bars all the way? Of course not. The moment will be 0 at the end. It's decreasing if it's simply supported. So you may cut half of them at different stages, depending on the length of the beam, right? So the answer I want to tell you, when we can terminate some of the bars, when we no longer need them, when the rest is enough. Theoretical cutoff point. Now the code is telling you, when you have that point, the theoretical cutoff point, add a little bit. For some issues, to be in the safe side, add a little bit. Either D or 12 dB. They tell you that. From the theoretical cutoff point, once you determine that one, they're telling you, add a length of D, the depth, effective depth, or 12 dB, 12 times the diameter of the bar. Now they tell you this length, the theoretical cutoff length, plus the D or 12 dB must be greater or equal LD. If not, then you have to have LD. Good? So if this is my theoretical cutoff point, and this is D or 12 dB, okay? Those lengths, both of those must be greater than LD. Is there anything else need to be greater than LD? Ryan? How about this, the remaining 2 bars? How about the remaining 2 bars? From here to the theoretical cutoff points must be greater than LD. So that now those 2 will develop a Fy for you here. See? Not easy, right, Glenn? You just need to be, you put things together, you come down. A lot of things together, a lot of them to comprehend. Structural analysis, the flexural design with the development length, with the deflection, everything coming together. Too much terminology to calculate each of them. Okay, you have to be organized and practice on doing it. Organized and practice on doing it. And not only calculating numbers. You know now, okay, I have the development length, so how do I apply it? Okay, how do I apply it? We will have one more lecture on the development length. Example. Span equal 30 foot. Slab equal 5 inch. Spacing between beams equal 8 foot. Half prime C equal 5 KSI. Y equal 60. Simply supported beam. Span here. Span 30 foot, simply supported beam. Okay. Dead load 1.2 kg per foot. Live load 0.9 kg per foot. Service. Cover 2 inch. Normal weight concrete, non-epoxy coated steel. All of these, whenever you need them, we'll assume them. Anything else? Any information that we need, we will assume. design the beam. It's a T-beam, by the way. And check deflection. So I'm going to do flexural design. If I have time, or you guys can, finish the shear design. Finish the shear design. Did you guys review the lecture that I taped over shear? Another example?
Not yet.
Did anybody take a look? You did? Is it helpful?
Yeah, that's all.
Yeah, it's an overhang beam.
Yeah.
So there's two locations. But you should have that, guys. 2 lectures on the shear is not enough. That's one more added lecture. And also there is a flexural design. Show you, you remember how, did you see how I loaded the front to maximize the positive, then I maximize the negative, where I start with this, then I just change the steel at the other location. It's important. The exam is next week. Still, it takes 1 week to understand 1 lecture. So what are you doing? What are you still waiting? Solution. That's the first. What's the ultimate, guys? By the way, this load includes all self-weight. This loading include, the dead load includes all self-weight, the slab and the beam. So W ultimate is 1.2 times 1.2 plus 1.6 times 0.9. How much is that?
2.88.
1.3 times 1.2 plus 1.6 times. Oh, I got it wrong.
How much?
2.88.
2.88 kip per foot. And ultimate 2.88 times 30 square over 8. That is
324.
324 kip foot. Good? Now let's see what we have for our section. Let's see what we have at this time. What's that? Be effective. Let's establish be effective. What's this one? 5 inch. Do you know anything else? Do you know anything else? No. We need to design it. We don't know this. We need to design it. But we know what's the slab. Right? The slab be effective is the result of 3. Span over 4, which is 30 over 4. 30 times 12 over 4. Distance between beam center line, which is 8 times 12, an inch. Or 16 times 5 plus B web. So the first one is how much? I need fast answers, guys, so we can move on. How much? 90?
Yep.
So what time we finish? 5:45? So we have more than 30 minutes, right? Okay, I'm gonna go slowly. So 90 inch? 96?
96 for the next one. No, 90 for that one. 96 for the next one.
96. And this one, how much this one here? 80. If BW is 10, this will control. We don't know BW yet. Okay, by the way, for guys, it's going to be 8, 10, 12, 14. That number. Look, think about it. If you have 8, you can accommodate, barely you can accommodate 3 bars. In terms of number 9, you will not be able to accommodate them. Because if you take 2 inch to cover side, that's 8 minus 4, 4 left, right? That's the center spacing. So if you have 3 bars, it would be really hard. So usually 8, 10, 12. If you have a limitation on the depth, it may go way big because your depth is limited. Here I'm not putting anything, so we are free to design any depth we want, right? So again, I'm going to assume it again. If it's 8, it's going to be 88. If it's 9, if it's 10, then I will control. So this is 80 plus B web. I'm going to assume this one controls. And I'm going to use either 10 or more. So my calculation is correct. I have no limitation on BW. If you have limitation on BW, you figure it out here. So this is done now. 9 inch. Good? Good. Now, what's raw? How we start now? What do you do?
Find a row target.
It's a design problem. Look, in any design problem, so far what did I teach you? So you don't keep looking.
Use row 0.05.
See what he said? The first thing you get raw 0.005.
So you know your fee is 0.05.
Either use 0.5 of it, or you use it all. If all will not be enough, we went with doubling. But if we think will be enough and the T-beam is a strong beam, I may go with half of that number, or 0.6 of that number, any number I want, as long as I am less than raw 0.005. If I use that row, then I can calculate B and D, B web and D, right? So locate or get the value of raw 0.005. 0.0203. 213. Why? Because F prime C is 5 psi. Some will make a mistake in here and will pick 0.0181 because that's for F prime C equal 4. Be careful what I'm giving you. I'm giving you 5. So that's that. For nice, I mean, it's look, if you use 0.02, you're fine. You're fine. That will decrease the required depth. You're fine. So I'm going to use. Someone said, is this used that required? No, I'm a designer. That's why I'm telling you it's a sample solution. It's up to you. The prices of steel are high. They're going to say, why don't you use 0.5 of that? No, as long as I'm using something less than that, more than raw minimum, I'm fine. And raw minimum for T-beams is raw minimum for rectangle.
Oh.
Very small. So I'm going to use 0.018. I'm going to say why 0.018? That's nicer to get R, right? From these tables. We don't want to end up with a calculation table. Okay? So that's what I'm going to use. If I use that, what's R? From the design aids.
943.
It's 943 PSI. This is in PSI. Now here we go. Now, how much my fee now? Glenn, you know what's my fee? It's 0.9 for sure. Because I'm using less than that. I'm using less than that. So it's for sure 0.9. Why I went with a high value here? Look, you guys, you understand what I'm saying? I'm trying to minimize D. For no reason, just for me. I don't want to go with D, but so the architect later on can tell me, hey, this is D. So you can come with even the full row like 0.02. That's absolutely fine. You can go with 0.015, say no limitation about this, so I don't care. I'm going to reduce the steel in my design. Not reducing the steel, it means I'm not reducing the steel. If you reduce the steel, you increase the concrete. If you increase the steel, you decrease the concrete. You know this, it's a balance. Okay? Now, do you remember this formula? PMN equal 0.9 R BD squared. So now PMN here, from structural analysis, you make an ultimate equal to this. 3, 2, 4, and pause for a second now. Pause with me for a second. This is Cape fault. Everything is there in, see, the R and PSI. Everything there is in pound inch. So this, right away, you multiply by 12,000. Okay. Right there. This is the mistake in applying this equation. The classical mistake. 12,000 to change it to inch pound. equal 0.9 times 943 BD squared. This will give you BD squared equal what?
4581.
4, 5,
81.
81 inch cube. Look, if B equal 10, what's D? It's my design. I'm gonna say, how is this? It's my design. I'm gonna make it 10. Nobody has anything to do with it. I mean, no limitation.
No. Yeah.
Square root of 458. How much we get? 21.4. Excellent. Good. So I'm gonna use h equal 24 to make it look nice. In other words, my d will be what? 22. Okay. If there is a requirement on h to be not to be more than 20, it means your d cannot be more than 18. It means you make your b bigger, or you fix your d and you calculate b. Is it clear, guys? It's so easy now. These things should be easy now. So use d equal 22. D equal 22 for h. H equal 24 inch, 2 feet. It's easy. And our b is 10 inch. Now you can say, oh, so what should I do now to calculate area of steel? Should I multiply this row by the 22 or by what? Look, what row we use? What is our row?
1, 0,
What's row? What row will we use?
0.018.
1A. That row, to get what we need over there, ask for B equal 10 and D equal 21.4. For us, because we are generous, we said we're going to use D equal 22. That's fine. But you don't have to multiply this for the rounded number. If you multiply this by the 21.4, that would be fine. That would be fine. Because anyway, now you're going to round it a little bit more to get the required area of steel. So AS equal 1018 times 10 times 21.4. This is, you see guys, now when you see something like that, don't think it's annoying or a mistake. It's fine. You may say 22, you may say 21.4. That's fine. That's fine. Be relaxed, comfortable. It's a design problem. It's concrete, guys. It's concrete. Made of stone. So AS equal
3.85.
3.
Yeah, 0.85.
You know there is something called 3.8.
We have 3.81.
Which is
Is that
5.
close enough?
Which is 5, right? 5 number 8.
It's 3 number 10s.
3 number 10 will give you that.
It gives you 3.81.
Which is fine.
That's close?
That's absolutely fine. I'm going to show you in a minute why.
Well, because we're taking 24 instead of
So
21.
select, yes. Select 3 number 10 AS equal how much?
3.81.
3.81 inch square. This is compensated by the D we have. Actually, you need to check this one, which is easy check, right? Easy check. I'm going to check it in a minute. We need to check this one. I'm going to check it for you. So our section now, we have it. Our section we have it. And the 9 is 9. Check VMM. First of all, what do we check, guys? A. Is it within the flange or not within the flange? So for rectangular analysis or non-rectangular analysis. By the way, the way I did it, the R thing I did here is for rectangular analysis. Be careful. It doesn't work if the analysis is T-beam. If the analysis is a T-beam analysis, the R method I used here doesn't work. But most of the time it works. That's why if they want to give you a T-beam example in the book, or I give you, usually they give you the flange is 3 inch and F prime C is 3 KSI. In a rare situation you will have a T-beam analysis requirement. So what's A? ASFY over 0.85 F prime C, be effective. The first time you check it from this side. If it's less than 5, you're good. So A equal what? 3.81 times 60 over 0.85 times 5 times 90. That's a small number for sure.
0.59.
0.59? See how small?
Really small number.
Are you sure?
That's way too small.
Could be. Could be, that's what you have.
Yeah, that's what it is.
Why is 90?
90 is be
Oh,
effective. Yeah.
1.6 you mean?
Yeah, sure. 0.6.
1.6. The smaller the A, the stronger the section. The smaller the A, the stronger the section. The stronger the section, because what's the arm? It's D minus A over 2. So the smaller the A, the stronger this arm between C and T. The higher the distance between T and C, when the A is smaller. So now phi mn equal 0.9 times 3.81 times 60 times 22 minus 0.6 over 2. Everything is divided by 12 to change it, because this is in KSI. To change it to kip foot divided by 12. This is slightly bigger than 324. 372? Was it 324 before? Or 354?
324.
See? 324. How much the ratio, by the way? 372 divided by 324. 1.15. Good. You can still decrease the steep a little bit, by the way, guys. You still can decrease the steep. You have a room. You have a room. So you see what I'm saying? Don't be like confused about, oh, no, I need to go for number 9 here or something in 2 layers. We still have a room. Go ahead.
What ratio is bad?
It's not, I mean, look, for this course, you know, I can't just teach you to have 50%. Not more than 15% in this course. Later on, up to 20%. After that, it's really time wasting money.
So this is as far as we can go. This
Yes.
is the 15%.
And then
Okay.
later on, when you go, it's okay if you go to 20% more, but don't go more than that.
Okay.
Don't go more than that, unless you know the construction guy is really bad. The guy who's gonna build it is a really bad guy, and the guys have no clue what they do. We're gonna end up with a concrete that will not give me 5 KSI. See the answer? Depend. Okay. You guys can you design this for shear? You should. Just draw the shear diagram. It's linear. Find the value of the critical section. Calculate VC. Okay. See how much VS needed at the critical section. Design the stirrups, the spacing right there. Then find the 3 regions. The region where the maximum spacing is needed, and the maximum spacing has 4 equations, and the region where the no stirrups are needed, which is when we have V ultimate less or equal PVC over 2. 3 regions.
To know the slab section thickness?
The first thing we design is the slab.
Okay.
That's the first thing we design in reinforced concrete. Slab, because we know the support of the slab is the beam. So this slab, if it's a slab, the support is the beam. Okay? So the thickness we have. And the thickness of the slab is determined such that the deflection doesn't have to be checked. Such that the deflection doesn't have to be checked. Now, good?
Yeah.
That answers? Now, with the question, the second question is check the deflection of this, right? Okay. Table in the new book 7.1 says if the overall depth of your bar, if the overall depth of your beam is greater than this depth or this number, deflection is good. You don't have to check. Remember that? You remember that?
Oh yeah, it's table 6 one for us.
So what does the look? That thing gives limitations or limits for solid one-way slabs or beams or ripped one-way slab. Our guy here is the customer we are dealing with is a beam, right? So we're in the second one.
I have a question. You did not check the spacing if it was greater than the cover. It's not. So I just want to know if you
What
have
spacing?
to check the space of the bar and check the width. Like check spacing.
To check if they fit
spacing.
with the cover and everything.
Oh, they fit for sure.
It fits, but when you get the clear space in the clear space,
dB, at least dB.
it's gonna be less than the 2 inches cover. That's why. No?
The clear spacing between the bars is determined by the maximum aggregate size, or like a common practice, not less than dB, the diameter of the bar.
Diameter of the bar or D is the cover?
No, they took the diameter of the bar, because the cover is different. The cover to the center was 2 inch, right? You take half of the number 10 from there, you take a stirrup around it also. So basically, if you have no limitation about, and remember, there's other limitations if you have it outdoor or exposed to the icers or that, they may tell you the cover must be at least 2.5 inch or something like that. But 3 number 10 can be fit within 10 inch wide beam. By the way, there is a table, and I may show you later on. It tells you based on the width, how many bars you can fit in there. There's one table in the design aids. How many bars you can fit in a given thickness. Okay, from each size. Good? So it says for simply supported beams, the maximum is simply supported beam L over how much, Austin? You have it? 16. So what's L over 16? 30 times 12 divided by 16. How much? 22.5. So if your beam depth H, when you deal with the deflection, it's H, is greater than this number, deflection will be okay. So is deflection okay? Believe it or not, that's a check. That's a check. And some guys, they even from the beginning, they pick H based on this table because they are scared to check the deflection. So they come here, they do okay, L over 16, let me use H equal 24 for sure. Then they go back and calculate the area of steel. That's fine. That's absolutely good design. That's fine. But I'm going to show you because the problem that I'm going to give you in the exam will not check on this one. It will check on the other one. So I'm going to show you even for this one, let's check the deflection. Okay? Let's check the deflection. But that's the check there, right? The check is right there. It's according to the ACI code. This beam with 24 inch will have no problem. But let's see how we do it. Okay, what's delta max for a simply supported beam? Again, keep asking this question, I'm going to get upset if you don't answer. I'm going to write it. That's the formula, 5W to the power 4 over 384 EI. Good? So what do you need in there? What do you need in there? What's EC, by the way? 57,000 Square root of 5,000. How much?
4030508.
40.
305.
That's it. This is KSI, right? What's ES? 29,000 KSI. What's M? 29,000 over 4030. Approximately.
7.2.
So we're going to use approximately 7. Okay? We're going to assume approximately 7 for our calculation. So EC is here. W is given. L is given. What's left for us? IE. That's the story. IE. Actually, I can give you a question, calculate IE for this section. I know if you calculate IE, you can do this because it's just like a number. So look at IE now. MCR over MA cube times I gross plus 1 minus MCR over MA cube I crack. Good? Look how many things we have in there. Okay, we're going to start one by one. We're going to start one by one. Need some fast guys with a calculator. Find I gross. We need Y bar, right? For this T. 90 times 5 times 2.5 plus 90 times 5 times 2.5 plus 10 times 19 times 9.5 and 5, 14.5. For the top part, I'm trying to find what's Y bar from the top. 5 times 90 times 5 over 2 plus 10 times 19 times the distance from the neutral axis from this one to the top. So it's going to be 9.5 plus 5, which is 14.5. If you don't know this one, go back attend statics. They are taking statics now. There's only 13 students. So you can understand a lot of stuff. So what's Y bar? 6. Now, by the way, when I say I gross, still is ignored. For I gross, still is ignored in the formula. This is the ACI formula, by the way. So I gross, each component equal. So that's our Y bar here. 6 inch. Equal. Look, we're going to do the same thing. The two components that we did. 90 times 5 cube over 12 plus 90 times 5 times, a lot of guys now will just get stunned. It's quick. 2.5 plus 1. That's the distance between the two. This is the parallel axis theorem. Plus 10 times 19 cube over 12 plus 10 times 19 times. Good? From the distance from the 9.5 to here, to this, it's 9.5 minus 1. It's good. Austin, you following? Okay. So what's I gross? $25,143.3.
43.
143.
Yes.
Yeah, doesn't give me these things after that. We're dealing with a huge number, and the error is really big. So don't worry about that. I told you the error in EC by itself changed from 22 plus minus 20%. That's our first guy in here. What's MA? What's the definition of MA? The maximum service load moment in the beam. What is WA, the service load? It's 1.2, right? Plus 0.9 equal 2.1. So what's MA? It's 2.1 times 30 squared over 8. You get that? How much? 8. How much? 2.1 times 900 over 8. 236. Keep foot. MA equal to 36. Keep foot. MA. We have this in here. We have this. Let's find crack. Calculate crack. I'm gonna ignore steel 2. The only reason I'm ignoring steel because it is a TB. So its effect is very small. In rectangular sections, you have to calculate what? IUT, I and crack transform. You know this, we covered it in details. But let us do this one. So look, FR equal M crack Y to the tension over I gross. Okay, over I gross. So M crack equal FR. What's FR? 7.45 square root of F prime C times what's I gross? Here we have 25,143. What's Y to the tension side? YT. What's Y? 18. It's 6 from top. This is the location of the tension. This is where we calculate FR, not at the top. This is where the crack will start. That's FR. So 18. And M crack is how much? It will be slightly bigger because the actual I will be more than that. Is there anything wrong? It was H minus Y bar, guys. It was H minus Y bar, which is H minus Y bar. In the formula I gave you before. How much? 7.5 times equal to 5,000. Oh, the number is confusing for you, right?
Conversion.
Divide by 12,000.
62.
60, good number. So I have this guy. I have this guy. I have this. The only thing left is I crack. Now, how we do it? Huh? The first thing you do when I ask you I crack is what? Get K. Get K. What's K? For n equals 7. No, it's given. It's calculated for you. Yeah. K and J are calculated for you guys. Yes, all of this. So what's K for 5,000? A prime C equals 60. KSI and n equals 7. Guys forget? Table A6.
Is it
Calculate K and A. From this table. Calculate it. How much you get? 0.392.
That's for K.
Good?
Yeah, 392.
Now what's KD? 392 times 22. So how much?
8.62.
8.62. Yeah? So this is your section. I'm making that exaggeration with the plan. It's just not to scale. So this is KD. You said 8.62. So this is the cracked section at the elastic. What do we have at the bottom now? What do we have here? NAS equals 7 times 3.81, you said? Right? That's your cracked eye. That's your cracked eye. Okay? The distance from here to here is 22 minus 8.62. And this is 90. And this is 5. Can you find I for that one? Are we still taping? Good. Okay, I'm not going to take this small piece, although I can. It's easy to do it. Okay, it's easy to do it. We'll take everything. We'll take everything. So I can equal the following. I'm going to start with the steel. It's NAS, which is 7 times 3.81 times the distance from there to there is 22 minus 8.62 squared. Done with the steel. Let's take the top piece. The top plus 1 over 12 times 90 times 5 cube plus 90 times 5 times 8.62 minus 2.5 squared. Distance from this to this. Right? We did not take it the other way. We took 1/3 because this was touching the base. We're going to do this for that here. Plus, look, plus 10 times 8.62 minus 5 cube over 3. That's the tiny piece in here, which I told you the other day you can ignore it. Not a big deal. I need an answer, fast answer. Two guys, I need two numbers. I mean two confirmation. Again, see guys? NAS, the distance to the neutral axis, the cracked section, square, plus that and that. But this is approximate, guys. It's a good approximation. It's a good approximation.
22724.
Yep. 2, 2, 7, 2, 4.
Yep.
Yes. That's what we get. Okay. Not a big difference from eye gloss. Not a big difference from eye gloss. Now what's I E equal? Okay, can you guys calculate for me the following? Someone calculate for me the following. 90 times 5 cube over 3. Keep it.
3750.
Keep it. Plus 7 times 3.81 times 19 squared. That thing, 7 times 3.81 times 19 squared.
It's huge.
I know.
13,377.
15,000? How much?
13,378.
13. 300,
80, or 78.
78. It's fine.
like this. This might not be accurate a lot. You know why? Because when KD is greater than the flange, this KD cannot be applied to this one. So what I said, we're going to assume the neutral axis at the bottom of the flange and calculate that. That's what I said the other day. And that's a reasonable number. If you do this one divided by that, the crack would be half what we have. Again, you know how we get to this number here? This number, since our KD is greater than, we calculate this number to be greater than the flange, so this number now is not a real number. You remember the value of A? Remember the value? This number, assuming this cross section is all rectangular, but it is not. But it's not. So we said for approximation, if that's the case, I said for approximation, if that's the case, take the cracked section to be the following. To be this, and the steel. You understand what I'm saying? It's not 19, it's 17, right? 22 minus 5 is 17, right? To here. And this is 9. You know why? Again, I'm explaining. When I check KD, that K is based on rectangular analysis. If it's more than HF, the thickness of the flange, it cannot be because we are assuming there is area that doesn't exist. I said for approximation, take your cracked section to be the full flange plus the steel there. And if that's the case, your crack, I crack will be 90 times 5 cube over 3 plus NAS, which is 7 times 3.81 times the distance from here to here, which is 17 squared. Usually, guys, the cracked section is half of the gross area. Half. Goes to half. So what's I cracked in this case? Cannot be analyzed that way. How much? Again.
11, 4, 5, 7. Yep.
11, 4, 5, 7. And you can tell I crack over I gross is how much?
4, 5, 6.
See? 45. You know why the analysis before did not work? The only problem with the analysis is this, we are assuming this one is away from the neutral axis, and this is a huge compression area. The other component of it, which is AD squared, give us a big number, which is not real, number. Okay? So that's your I crack. Now what's I effective? Give me the numbers. I'm cracking is what? 62. Allowable is 236. I gross is what? 25, 143, plus 1 minus 62, this is cubed by the way. 62 over 236 cube times 11, 4, 5, 7. And the disappointment now will be, guess what? That's IE is very close to I crack. Did you do it?
$11,705.
11,705.
That's pretty close.
So, for your reference, if this is the minimum. I mean, I effective is always bigger than I crack. It's very close to I crack. You know why? Because usually this ratio here is very small. So this number, this factor, when multiplied by a gross, is a small factor compared with what you have in here. Okay, guys? Now this one must be checked against. Now you can calculate delta for the live load, the service live load. Check delta for me for the service live load, and go to table 7.2 and see what's the requirement of the immediate deflection due to live load, and check if they are good or not. Okay, you do this on your own. That's for sure a fact, a problem in the exam. Okay. So check it. If you have any questions, let me know. So next lecture, I'm going to continue with what now? With the development things.